Okay, let's go ahead and look at the additional practice for Chapter 11. So as a reminder, in Chapter 11, we're looking at VSEPR. So how do these molecules rotate in 3D space? We're looking at polarity, we're looking at valence bond theory, and we're looking at molecular orbital theory. So first, let's start out with some molecular geometry. Let's draw the molecular geometry, determine the bond angles and polarity of the following molecules. NH3. If you're not comfortable drawing straight to the structure, draw the Lewis structure first. I will draw Lewis structures first for some of these, but eventually I'm just going to start drawing the molecular structures when I find them to be faster. So for NH3, we have 8 valence electrons, nitrogen with a lone pair bonded to 3 hydrogens. When I look at this, I see that I have 1, 2, 3, 4 areas of electron density. Which means I have an electron geometry that is tetrahedral. I'm going to redraw this molecule in that fashion. Now I look at this and I say, okay, that lone pair is going to affect the bonds. I also know tetrahedral has bond angles of 109.5, but that lone pair is going to push on these bonds, making them closer together. So what I'm actually going to have is nitrogen here. You can leave the lone pairs on the nitrogen if you want. I don't care, but most people draw it like this. We call this Trigonal Pyramidal because it's forming a triangular shape between the hydrogens, but a pyramid to the nitrogen above. And the bond angles are less than 109.5 degrees. Oh, and polarity. Sorry. Polarity, yes, this is a polar molecule. Nitrogen is more electronegative than the hydrogen is. And it's not a symmetrical compound, so it is a polar molecule. We are pulling that electron density towards the nitrogen, or you could say the vector is going towards the nitrogen. When I look at CCl4, carbon has 4 valence electrons, each chlorine has 7, so 32 valence electrons. Connect your atoms and give your outer atoms their octet. Check to make sure your central atom has its octet. It does, so we are good to go. We have 1, 2, 3, 4 areas of electron density. So we're talking about it compared to the central atom, the atom we're looking at. So we know my electron geometry is tetrahedral. Which is 109.5 degree bond angles. Go ahead and draw this in a tetrahedral shape. Oops. Not hydrogens, chlorines. Carbon tetrachloride. Not a very nice chemical. I'm not going to draw lone pairs in the outer atoms because I don't need them. They were drawn there for the Lewis structure to determine where the electrons were going, but I don't need them in my VSEPR shape. I don't have any lone pairs, so my compound stays tetrahedral for molecular geometry. So remember, electron is what do the electrons decide the geometry is? Molecular is what is the molecule's actual geometry, with bond angles of 109.5. Now, chlorines are all more electronegative than carbon. So all of these are more electronegative, but they're all pulling on each other. It's a perfectly symmetric compound. which means it is nonpolar. And CHCl3, I'm going to shrink these down for shape, for size too, just so we can fit more on here a little more comfortably. So CHCl3, carbon has 4 bonds, or 4 valence electrons. Hydrogen has 1 valence electron. 3 chlorines. Chlorine is 21. Overall, what is that? 21 plus 4 is 25, 26 valence electrons. Connect my outer atoms. Give my outer atoms their octet. Check to make sure my central atom has its octet, and it does. So we are good. We've got 1, 2, 3, 4 areas of electron density. Which means my electron geometry is tetrahedral. 109.5 degrees. Draw this into your molecular geometry shape. Carbon bonded to a hydrogen and 3 chlorines. Again, I'm not going to write the lone pairs in the chlorine here because they don't affect my geometry. They're outer atoms. So this stays tetrahedral for its molecular shape, which means 109.5 degrees. But now I have to look at polarity. Chlorine is more electronegative than carbon or hydrogen, which means that these chlorine atoms are pulling electron density to themselves, and hydrogen can't counteract that. This is a polar molecule. According to VSEPR, what is the molecular shape to the bromate ion BrO3-? So I don't know this one by the top of my head. So bromine, 7 valence electrons, 3 oxygen, 3 times 6 valence electrons. Is that 18, 19, 20, 25? Plus 1 extra valence electron for that negative charge, 26 valence electrons. Connect your outer atoms. Give them your octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 2 valence electrons left. Put them on your central atom. Check to make sure your central atom has its octet, and it does. Now you can check formal charge here. We see formal charge. So remember oxygen has 6 valence electrons. Each oxygen here has 1 bond and 6 lone pair electrons, so each oxygen is a -1 charge. Bromine has 7 valence electrons, 3 bonds, and 2 lone pair electrons, so +2. Overall, it adds up, but I could also double bond these two, minimizing my formal charge. Now, these each have 0 formal charge, and my 1 oxygen has a -1, giving my overall -1 for the thing. It doesn't really matter, though, because I'm not caring so much about the Lewis structure right now. I'm caring about the molecular shape. Molecular shape tells me to treat double bonds the same as single. So 1 area of electron density, 2 areas of electron density, 3 areas of electron density, 4 areas of electron density. Which tells me my electron geometry is tetrahedral, which has 109.5 degrees. Now, that's not my molecular shape. I need to draw that into my VSEPR shape. So I've got a lone pair, oxygen, oxygen, and oxygen. My molecular geometry, therefore molecular shape, is called Trigonal Pyramidal. And that lone pair is going to push on those bonds, so the angle will be less than 109.5 degrees. Determine the molecular geometry and polarity. NH3, I think I drew NH3 in the first example, but if I draw out NH3, if you're not sure I did this, look back at the first example where I did draw this out, or work through this yourself, but you should find that this is trigonal pyramidal. And it is polar. O3. This is called ozone, by the way, in case you guys care. Ozone, if you draw this out, you're going to find it has a resonance structure. You can either have oxygen double bonded on this side or double bonded over here. But what you're going to find is 1, 2, 3 areas of electron density, which means it's going to follow a trigonal planar shape. But that lone pair doesn't count into the structure. It's just the trigonal planar shape. So we call this bent. And because it's based on trigonal planar, its bond angle will be a little less than 120 degrees. But it is a polar molecule because of the shape. SO2. Looks like this for a Lewis structure. So 1, 2, 3 areas of electron density. Again, trigonal planar shape here. Lone pair up here. It's also called bent. Based on trigonal planar, so less than 120 degrees. And this is also polar. BRF3. If you look at BRF3, you're going to have 28 valence electrons. I'm going to draw it up here because it's just going to take more space. Connect your fluorines. And you're going to find that it has 2 lone pairs to make up to the 28 valence electrons. So this is 1, 2, 3, 4, 5 areas of electron density. Which means its electron geometry is called Trigonal Bipyramidal. Remember, for trigonal bipyramidal, that's when you can have an axial or equatorial position. Axial are above and below, equatorial are along your equator. Your lone pairs go to the equatorial positions. So lone pairs on your equatorial positions. Fluorine's elsewhere. Now, that's probably hard to see the way I wrote that. Let me write it this way instead. Write your lone pairs over here just so you can see a little bit better. The reason I rewrote that is this is what we call T-shaped. It's like a T. Again, these are called this and this position. Equatorial. This is axial. This is axial. Axial are 180 degrees apart. They're 90 degrees to my equatorial, and the equatorial are 120 degrees apart. Because I have the lone pair there, it's probably a little bit smaller. Two lone pairs actually make it even smaller. And fluorine is more electronegative than bromine. This is polar. And CO2. CO2 is carbon double bonded to two different oxygen molecules. This is linear. And even though each bond is in fact polar, this is a non-polar molecule overall. How many pi electrons are found in the amino acid aspartic acid? Remember, pi electrons come into play whenever we have a double bond. So I've got a double bond here. I've got a double bond here. There's 2 pi electrons here. There's 2 pi electrons here, which means in total I have 4 pi electrons. Which of the following molecular geometries has 6 atoms joined to a central atom? Hexagonal is not a structure. Trigonal planar has 3. Trigonal bipyramidal has 5. Octahedral has 6. Which of the following molecules is nonpolar? Well, we've just written out NH3 twice, so it's definitely not NH3. If you're not sure, go back to number 1 or number 3. Xef4, if I drew this one out, I would find it to have a square planar structure. Square planar is perfectly symmetrical and nonpolar. Let's make sure it's the only one. Water is a bent structure and polar. Ch3Cl. Polar. And CH2Cl2, dichloromethane. Also polar. For each molecule, what is the MO electron configuration, the bond order, and the magnetic character? So remember, to do this, we need to first find the electron configuration. So for nitrogen, 1s2, 2s2, 2p3. If I have 1s2, 2s2, 2p3, this would be how I would write up an atomic orbital. So atomic orbital is just one atom. For this, I'm going to write up 2 atoms and combine them for molecular. So I've got the 1s with 2 electrons. 2s is higher in energy, so this is my energy scale increasing here. And 2p. And I have 3 2p electrons. I also have this for my second nitrogen. So I have 1s over here with 2 electrons, 2s with 2 electrons, and 2p with 3 electrons. Remember, parallel before paired, so we fill them up singly before we pair them up. But to write so what's going to happen here is, again, this portion, just listed like this, is your atomic orbital. Okay? I'm going to combine 2 atomic orbitals to find my molecular orbital, because it's the orbital of a molecule. Every time we do this, we combine 2 orbitals and 2 come out. So like we're combining 2 1s orbitals, we're getting out 2 molecular orbitals, specifically in the s. We're going to create 1 bonding and 1 antibonding. So the bonding will be lower in energy, the antibonding is higher in energy. We call your bonding for 1s a sigma, and this is specifically sigma 1s because it came from the 1s orbitals. We then fill in your electrons, and you've got 4 electrons in, 4 electrons out. Each orbital can hold 2 electrons, as we've always seen. 2s does the same thing. We have, and then I'm sorry, the antibonding is labeled sigma star, and then 1s because it came from the 1s. So the star means antibonding. The 2s's combine to form a sigma 2s and a sigma star 2s. So bonding and antibonding. Again, remember, the star tells me antibonding, and it's higher in energy. Now, for nitrogen and chlorine, the next part works a little bit differently. The p orbitals, we have 3 p orbitals that go in from each side, which means 6 p orbitals in, 6 come out. But the way these combine, we have to think about how they're combining. And so I'm going to erase a little bit down here just so I can fit some space in here. When you think about your p orbitals, you have 3 p orbitals. You have your px, your py, and your pz. If 2 px orbitals bond to each other, this is a head-to-head overlap. And this is called a sigma bond. If 2 py orbitals overlap, this is a side-to-side overlap, which is called a pi bond. And if 2 pz orbitals overlap, this is also side-to-side, so also a pi bond. So 2p, we have 3 p orbitals from each side that go in. So 6 p orbitals in, 6 p out, but, oops, wrong button. 2 form sigma, and the other 4 form pi. Within sigma, we will have a sigma and a sigma star. Within pi, we will have a pi and a pi star, bonding and antibonding. Nitrogen and oxygen is where it flips on the table. So remember, nitrogen and oxygen next to each other on the table. This is where it's split on the way your molecular orbital diagrams look. Nitrogen is going to fill your pi bonds first, then your sigma for bonding. So your 2p pi bonds are lower in energy than your 2p sigma bond. For antibonding, it's your pi's first, then your sigma, no matter what. This is a pi star, 2p, and this is a sigma star, 2p. 6 electrons go in, so 1, 2, 3, 4. Truthfully, I could fill them that way so I knew it was going to happen. You should do them individually first. 1, 2, 3, 4, 5, and 6. This is the molecular orbital diagram for N2. What is the bond order? Bond order takes the number of bonding electrons and subtracts the number of antibonding and divides it by 2. Now again, I kind of tend to, if your orbital is completely filled like this, I kind of ignore it because it's got the same number of bonding and antibonding orbitals, so they just kind of cancel each other out. You can continue to ignore that, or you can calculate that in. I don't really care, but I'm going to ignore it. I'm going to just look at the orbital that's not completely filled. I see that I have 2, 4, 6 bonding electrons, and I don't have any antibonding. So 6 divided by 2 is 3. My bond order is 3. What does that mean? Bond order of 3. That means between 2 nitrogen molecules, I have a triple bond. And if I drew out the Lewis structure, I would find that, yes, nitrogen does triple bond to itself. Lastly, we want to know your magnetic character. What does magnetic character mean? Magnetic character is basically, will it respond in a magnetic field? I determine this by finding out if the molecule is paramagnetic or diamagnetic. Which one is it? Paramagnetic means unpaired electrons. Diamagnetic means all electrons paired. Here in nitrogen, all of my electrons are paired, so it is diamagnetic. Diamagnetic is repelled in a magnetic field. So it's not a magnet. It doesn't act. It's not attracted in a magnetic field. Okay, so I need to erase all this so I can write out Cl2, so please pause the video if you need to. But let's go ahead and work on Cl2. If I look at Cl2, remember chlorine, 1s2, 2s2, 2p5. So I'm going to do what I did before. I'm going to draw out my atomic orbitals first. I've got the 1s, 2s, 2p, 1s, 2s, 2p, oh, and I know I talked about how in bonding, the reason that P forms 1s and 2p's is because our px's overlap in a sigma bond, whereas our py and pz overlap side to side, which is a pi bond. So sigma and pi. And we saw this in lecture as well, but sigma bonds, s orbitals, are spherical and they overlap in a sigma, which is why I form those sigma bonds. So let's put in our electrons. Chlorine, 1s2, 2s2, 2p5. 1s2, 2s2, 2p5. They're going to form 2 atomic orbitals in, 2 molecular orbitals out. Sigma is lower in energy, and this is a sigma 1s specifically. Sigma star is higher in energy, and it's sigma star 1s. 1, 2, 3, and 4. Our 2s also combine 2 atomic orbitals in, 2 molecular orbitals out. sigma 2s, sigma star 2s, 1, 2, and 3 and 4. Now onto my 2 p's. Remember, the p's are going to form 2 sigma bonds and 4 pi bonds. One bonding sigma, 2 bonding pi, 1 antibonding sigma, 1 antibonding pi. But now we're to chlorine. And again, we talked about how nitrogen and oxygen is where it splits on the table. In nitrogen, I filled my P, then my S for bonding. Once I hit oxygen, I fill my sigma, or my S orbitals, I fill my sigma, then my pi second. So my sigma 2p is lower in energy than my pi 2p. Up here, pi star 2p and sigma star 2p. The top half is the same no matter what element you're looking at, but the bottom half does flip. Put your electrons in. We have 5 plus 5, so 10 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So what is your bond order? Again, I'm going to ignore the 2s and 1s molecular orbitals just because they're going to cancel each other out. So I'm going to look up here and I'm going to say, okay, I've got 2, 4, 6 bonding electrons. And I've got 2, 4 non-bonding electrons. Divide that by 2. 6 minus 4 divided by 2 is 1. That tells me that there is 1 bond in the Cl2 molecule. If I drew out the Lewis structure, I would also predict that as 1 bond. And what is the magnetic character? This is diamagnetic because it has no unpaired electrons, which also means it will be repelled in a magnetic field. Okay. According to VSEPR theory, the bond angle of the SeF3 anion is expected to be closest to what? Well, let's draw out this molecule. I don't know where I put my notes, so we're going to do this the long way. I know selenium is underneath oxygen on the table, so it has 6 valence electrons. I have 3 fluorines, 3 times 7 valence electrons. That's 21 plus 6 is 27. Plus a negative charge here gives me 1 extra valence electron. Overall, 28 valence electrons. Se in the center. It's more electropositive than fluorines. It's going to go in the center, plus it's listed first. Connect your fluorines. Add your lone pairs. So I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. 28 electrons. This has 1, 2, 3, 4, 5 areas of electron density. Which means the electron geometry will be Trigonal Bipyramidal. I'm going to redraw it in that configuration. Trigonal Bipyramidal is the one that has axial and equatorial positions. And the lone pairs will always go equatorial because it's the largest space for them. Now that I have this drawn out, I see this is called T-shaped. And this is a polar molecule because it's an unequal distribution of charge. But what is my bond angle going to be closest to? Well, what bond angle do you want to talk about? The axial bond angle is normally 180 degrees, but because of the lone pair, it will be less than 180 degrees. Not a lot, but a little bit less. The bond angle between here is usually 90 degrees. It'll be a little bit less because of those lone pairs. And the bond angle between these will be a little bit less than 120 degrees. The bond angle between the lone pairs will actually be a little bit greater than 120 degrees. So it depends on which bond angle you would like to discuss, what the bond angle will be. Use VSEPR to predict and draw the 3D structure of each compound and specify polarity. So NH3, ammonia, has 8 valence electrons. Connect your atoms. Count up your area of electron density. We have 4 areas. Which means my electron geometry is called tetrahedral. Bond angles for tetrahedral, 109.5 degrees. I realize the question doesn't ask for bond angles, but it's always good to practice. Let's redraw this in a tetrahedral shape. You can rub the lone pairs or leave them off, I don't care. But we see once we put this in a tetrahedral shape, our molecular geometry is called Trigonal Pyramidal. We've got a triangular shape between the hydrogens, and they're forming a pyramidal shape, or pyramidal, for where you want to pronounce that word, to the nitrogen. So hence, trigonal pyramidal. Bond angles will be a little bit less than 109.5 degrees just because that lone pair. And this molecule is polar. Nitrogen is more electronegative than hydrogen, so it's pulling the electron density towards itself. Or you can say partial negative, partial positive. Xef4. Let's see, sulfur has 6 valence electrons, 4 fluorines, that's 28, plus 6 is 34. Sulfur in the center. Connect my 4 fluorines. Give my fluorines their lone pairs. And once I do this, I realize I still have one set of 2 electrons remaining, so they will go on my central atom. 1, 2, 3, 4, 5. 5 electron dense areas. Therefore, my electron geometry is trigonal bipyramidal, which has 3 different bond angles. It has 90-degree bonds, 120-degree bonds, and 180-degree bond angles. Let's go ahead and put this into its molecular geometry so we can see its actual shape. Remember, trigonal pyramidal is the one time we have to pay attention to where the lone pairs are going. Otherwise, the positions are equivalent, but on trigonal bipyramidal, they are not equivalent. We have axial, which is the axis as written here, and we have equatorial, which is the equator as written here. Your lone pair always goes equatorial. This is called a seesaw. And this will be polar. It is not perfectly symmetric. The fluorines are pulling. Sulfur is more electropositive than the fluorines are. And again, you don't have to draw the lone pair in here if you don't want to. Some people see it better, some people don't. That should be a negative. That should be a positive. So yeah, your fluorine is more electronegative than your sulfur. And last on this page, we've got BrF4-. Bromine has 7 valence electrons. Fluorine has 7 each. So there's 35 electrons plus the negative charge is 36 valence electrons. We've got bromine connected to 4 fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, and 36. So we have 2 lone pairs on our central atom. 1, 2, 3, 4, 5, 6 areas of electron density. The electron geometry here is octahedral, which means my bond angles are 90 degrees. In a base geometry, this does have lone pairs, so it will not be 180 degrees, or it will not all be 90 degrees. Draw out your structures. Now, if you're dealing with an octahedral structure in lone pairs, it's easiest to see it if you put the atoms on your wedges and dashes first, and then put any lone pairs, put any atoms that are left on the axial, looks like an axial position. It's not truly axial, they're all equivalent, but draw them there because it's easier to see it that way. In this case, I've got a lone pair here and a lone pair here. This is called square planar. And this is perfectly symmetric because it's bromine bonded to 4 fluorines. Why do I care that it's perfectly symmetric? Because perfectly symmetric molecules are nonpolar. According to VSEPR, which of the following molecules or ions is expected to have a tetrahedral geometry? Well, let's draw them out. Xef4, xenon has 8 valence electrons, fluorine has 7, there's 4 fluorines, 28 valence electrons of fluorine plus 8 gives me 36 valence electrons. When I give it all their lone pairs, I find that I still have 2 lone pairs left that need to go to the central atom. So it's just like the one we just looked at, where it's a square planar geometry. SF4. Fluorine, 7 valence electrons, and there's 4 of them, so 28. Sulfur has 6 valence electrons, 28 plus 6 is 34. Add your octets on your outer atoms. So I've used up 8 electrons so far, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Got one lone pair on my central atom. This is a trigonal bipyramidal base structure. So my sulfur, got my fluorine here, and then I've got my equatorial positions. Fluorine, remember your lone pair has to go octahedral. That is what we call seesaw. Okay, silicon tetrachloride, SiCl4, chlorine, 7 valence electrons, and there's 4 of them, so that is 28. Silicon is underneath carbon, so it's got 4 valence electrons, so we've got 32 valence electrons here. Used up 8 electrons, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. No more electrons. My central atom has its octet. This is a complete Lewis structure. Draw this into your VSEPR shape. silicon. This is tetrahedral. So we know number 3 is, let's just make sure that number 4 is not. IF4 plus, iodine and fluorine are both halogens, which means they both have 7 valence electrons. 4 fluorines and 1 hydrogen, 4 fluorines and 1 iodine. I keep saying hydrogen, I mean iodine. Iodine is a halogen. Whatever I said a minute ago, it's not. Iodine and fluorine are both halogens. They both have 7 valence electrons. So 4 fluorine and a hydrogen, that's 5 atoms, 7 valence electrons each, that's 35. It's got a +1 charge, which means it has 34 valence electrons. Go ahead and draw it out. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. Central atom will have a lone pair. You may already recognize that it's a seesaw, just like SF4, but let's go ahead and draw it out just in case. You got your iodine connected to your fluorines. Remember, this is the one structure it matters where you're putting your atoms. Atoms can go anywhere, but your lone pair can only go on an equatorial position. It can only go on one of these 3 positions. I tend to write it on the side like that because for me it's easier to see that it is in fact a seesaw structure. What is the molecular shape that VSEPR predicts for IF5? Iodine and fluorine are both halogens, which means they each have 7 valence electrons. So I have 6 atoms with 7 valence electrons each. 6 times 7, 42. Put your iodine in the center, it's the least electronegative, and fan out your fluorines around it. Add your lone pairs. You've used up 2, 4, 6, 8, 10 electrons so far. 12, 14, 16, 18, 20, 22, 24, 26, 28. Hold on. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 20. Yes, I am right. Okay, 30, 32, 34, 36, 38, 40, and 42. Sorry, guys. I was counting so fast I was losing track of what I was paying attention to. I have a lone pair on that iodine, but 1, 2, 3, 4, 5, 6 areas of electron density. Which means my electron geometry is going to be octahedral. So if I draw this out in an octahedral shape, I always recommend putting your atoms out and your wedges and dashes first. You can decide from there if you want your lone pair to go above or below. I tend to put, if there's only one pair, I tend to put it below and then this above. This is a little harder to see, but this is called, molecular geometry here is called square pyramidal. This is a polar molecule. You've got your square shape here. Remember those wedges means it's coming out of the board at me. The dashes mean it's going behind the board. So it's forming a square that's perpendicular to the plane of the paper. But they're forming a pyramid to this atom up here. Hence the word square pyramidal. Which ion is planar? NH4 plus, CO3 minus, SO3 minus, or ClO3 minus? Or are all of these planar? First, you should know the names of these, right? They are polyatomic. So let's go ahead and look at ammonium first. Ammonium has 8 valence electrons. This is its Lewis structure. So it's got 4 areas of electron density. If I draw that into its shape, I see that this is tetrahedral. What about CO3 minus, also known as carbonate? If you draw this out, you should find this structure. You can put your lone pairs here if you'd like. It does have resonance structures, but they're completely equivalent, so I'm just going to draw one of them. But there are 3 areas of electron density. Remember, a double bond counts as one area. So this draws out just like it's already written. This is what we call trigonal planar. So this ion is planar, but are any of the others? SO3 minus, sulfite. Let's see, I don't know that one off the top of my, or by heart. So 3 oxygens, 6 valence electrons each. A sulfur also has 6 valence electrons. So 4 times 6 is 24, plus a -2 charge, 26. And 26. This will form some double bonds. It's going to form one double bond like that. Now everything has its octet. Formal charge is minimized on 1 oxygen, 1 sulfur. The other 2 oxygens each have a -1 charge. They're happy to have a -1 charge. Second most electronegative element on the table. Yes, resonance exists, but the structures are equivalent, so I'm not going to draw them all out. But I've got 1, 2, 3, 4 areas of electron density. So when I draw this out, the double bond here, if you really want to keep the double bond, doesn't matter. But I have a lone pair up here. That lone pair causes this to be called Trigonal Pyramidal. It's sort of like, actually not sort of, it's just like the structure for ammonia. Lastly, ClO3 minus, chlorate. 3 oxygens is 18 valence electrons, plus a chlorine is 7. So 18 plus 7 is 25, plus a negative charge. Brings me to 26 valence electrons. Two, 4, 6, 8, 10, 14, 16, 18, 20, 22, 24, and 26. You're going to have them on the central atom. So just like what we saw for sulfite, this is going to follow a trigonal planar, or trigonal pyramidal structure. So B, is carbonate, is the one that is planar. For the molecule ClF5, determine your molecular geometry, hybridization of the central atom, and whether or not the molecule is polar. So pulling all these pieces in, just keep practicing these, okay? ClF5. Chlorine and fluorine are both halogens, so that's 6 atoms that have 7 valence electrons each. 6 times 7, 42. Cl, connect to your fluorines. Add your lone pairs. I've used up 10 so far. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and 42. I will have a lone pair on my central atom. 1, 2, 3, 4, 5, 6 areas of electron density. Which means octahedral for my electron geometry. The electron geometry and the molecular geometry only match when you don't have a lone pair there. So because there is a lone pair here, I know they're not going to match. For octahedral geometry, I like to write my wedges and dashes with my atoms first. You can do it however you'd like. All the bonds are equivalent. It just makes me see it better. The F, and then I have a lone pair down here. This molecular geometry is called square pyramidal. The molecule is, in fact, polar. And what is the hybridization of the central atom? Hybridization deals with how many areas of electron density are there, whether that be a lone pair or a bond. There are 6 areas of electron density. So I need S, P, 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 that's 1, 2, 3, 4, D, and D, 5, 6. It is sp3, d2. Why do I only have one s? Because there's only one s. When you look at the orbital shapes, there's one shape for s. It has one orbital. P's have 3, px, py, pz. D's have 5, F's have 7. So sp3d2. If I was going to try to draw out the structure, that means that all 6 of these orbitals are hybridized to be equivalent. Here I have a lone pair. Here I have a fluorine atom with a sigma bond overlap. Here I have a fluorine atom with a sigma bond overlap. Here I have a fluorine atom with a sigma bond overlap. Here I have a sigma bond to a fluorine. And here I have a sigma bond to a fluorine. Now someone may ask, why does fluorine look like that? Because fluorine is valence electrons, 2s2, 2p5. The 2 s's are full. All that's left is a 2p5. So I've got a p orbital it's trying to bond. It's going to bond by a sigma bond with a head-to-head overlap. The chlorine here is hybridized. But the fluorine doesn't have to hybridize. It's an outer atom. Predict the molecular geometry and bond angles of SiF5-. So let's see. 5 fluorines, 5 times 7, 35, plus silicon is 4, so we're to 39. Plus a -1 charge, we have 40 valence electrons. Si, F, 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 F. I've used up 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. No extra lone pairs left over. All of my atoms have an octet or more. Silicon can have more than an octet. Everything's happy. So I have 1, 2, 3, 4, 5 areas of electron density. Which means my electron geometry is trigonal bipyramidal. So I'm going to go ahead and draw it in that shape. Axial are the axis, equatorial, my equator. And I see that my molecular geometry is also trigonal bipyramidal. Again, electron geometry and molecular geometry will match each other if you don't have a lone pair. They only change when a lone pair is present. The angle between sp3 hybridized orbitals is closest to. sp3 means it's tetrahedral. So you are looking at 109.5 degree bond angles. Okay, I really like this question. It's a challenge question out of the end of my textbook, the textbook I had when I was in Gen Chem, but I really, really like it. Some students are like, ugh, I don't want to do this. But honestly, this is a great question to prepare getting ready for your final, pulling together all this information. I mean, this class is a cumulative class. Let's see if you can pull together the concepts you've learned. That's what this question is doing. Since a molecular compound is composed of 58.8% xenon, 7.2% oxygen, and 34.0% fluorine by mass, if the molecular weight is 223 grams per mole, what is the molecular formula? So I've got some numbers here I'm going to need. I want to know molecular formula. Let's highlight that into I want to know molecular formula. What is my Lewis structure? And predict the molecular geometry using VSEPR and describe bonding using valence bond theory. So lots going on here. But That's what I like about the question. It's pulling in a lot of different concepts for you guys. So, 58.8% xenon, 7.2% oxygen, 34% fluorine. I want you to assume you have a 100-gram sample, because then you can say that you have, for xenon, 58.8 grams of xenon. Determine the moles. 1 mole of xenon is 131.29 grams of xenon. This gives you 0.448 moles of xenon. If I look at oxygen, I have 7.2 grams of oxygen in this 100-gram sample. 1 mole of oxygen to 16 grams of oxygen gives me 0.45 moles of oxygen. And fluorine. I've got 34.0 grams of fluorine. Fluorine weighs about 19 grams. This gives me 1.79 moles of fluorine. Divide all your numbers by your smallest number, which is 0.448. And I see I get 1 xenon, about 1 oxygen, and about 4 fluorines. So my empirical formula here, Ch3cho, Xef4. If I looked at the molar mass here, xenon, 131.29 grams per mole, oxygen, 16.00 grams per mole, 4 fluorine, 4 times 19.00 grams per mole. That equals up to about my molecular geometry. It's off. If it's off at all, it's just by rounding. So I know that I have a molecular and empirical formula that match each other. So Ch3cho Xef4 is my structure. I figured out the molecular formula. It's right here. Next, I want to figure out the Lewis structure. Xenon has 8 valence electrons, oxygen has 6, and I have 4 fluorines at 7 valence electrons each. So what is that? 28, 30, 34, 42? 42 sounds right. Let's draw this out. If all your outer atoms are octets, I've used up 10 electrons so far. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Put your extra electrons on your central atom. 42. I've used up all my electrons now. Check your formal charge, and if you check your formal charge, you're going to find that oxygen and xenon are not exactly happy. So oxygen is going to donate a pair of electrons here to form a double bond to the xenon. When it does this, now everything has a 0 formal charge, which is what we want to see. We want to minimize formal charge if we can. That's my valid Lewis structure. Let's predict your molecular geometry. Well, I have 1, 2, 3, 4, 5. Remember, double bond is 1. 6 areas of electron density. Which means my electron geometry is octahedral. But I do have a lone pair there, which means my electron geometry and molecular geometry will not match. I'm going to rewrite this into my molecular geometry shape. And I find that I have square pyramidal. I do, however, have 6 areas of electron density, which means that my hybridization needs to be described by 6 different pieces. S, P, 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 D, D. 1, 2, 3, 4, 5, 6. SP3D2, octahedral. If I drew that out, it's lone pair here. It's sigma bonding to a fluorine here. 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 It's very hard for me to write upside down. Sigma bonding to an oxygen here. But then it's also double bonding to oxygen. So this oxygen is actually hybridized into an sp2 shape. Where it's got 2 lone pairs here and here. And then we have a pi bond system. Double bonding your xenon to your oxygen. Technically, it didn't ask me to draw it there. Technically, it asked me for this. For this. Not even actually for that structure. For this. That is the challenge problem, though. That's one of the, is challenging. Not as challenging I can get, but one of the most challenging I can do. To ask you guys the questions, but I promise you have all the resources to do it, and I really would encourage you to try it, because I think that you'd be able to do well with it. Okay, let's go ahead and work a few examples doing valence bond theory, sketching out the way these look. So, sketch the following using valence bond theory, showing sigma and pi bonds and hybrid orbitals. We have ethanoic acid. So we're getting into what we learned with chapter 10 with naming of these organic compounds into the structures. I see oic acid. I know that oic acid means that I have an R group attached to a carbon, which is bonded to an OH and double bonded to an O. But this tells me I have 2 carbons total, which means that this R must be a carbon, and I'm going to give that carbon enough hydrogens to make it neutral, meaning 0 formal charge, giving it 4 bonds. This is my structure of ethanoic acid. Now, when I look at this, how do I know how to describe the valence bond theory? Well, here's the trick. There's multiple central atoms, and each central atom has its own hybridization. Tetrahedral here, sp3. sp2, because I've got 3 bonds total. 1 is a double bond. This oxygen has 2 lone pairs, even though I didn't draw them out. Technically there. So this oxygen is sp3. This oxygen has 2 lone pairs and a double bond, so it is sp2. So let's go ahead and try to draw this out. Carbon, that's sp3 hybridized, is a tetrahedral shape. It's bonded to 3 hydrogens through a sigma bond. It's also singly bonded to a carbon atom that is sp2 hybridized. sp2 means it's a trigonal planar structure. These are sigma. But this bond is a sigma bond. It is a single bond. This carbon is double bonded to an oxygen and singly bonded to another oxygen. So, 1 oxygen it's bonded to is also sp2 hybridized, which is square planar in shape. This is a sigma bond. And that oxygen has 2 lone pairs in its other lobes. That carbon is also bonded to a second oxygen, which is tetrahedral in shape. It also has 2 lone pairs. And it is bonded through a sigma bond to a hydrogen. So this is sigma as well. Now I'm not quite done. I do have a pi bond here that I need to specify. So this carbon that is sp2 hybridized, I'm going to draw it like this, has a pi bond in here. This oxygen also has a pi bond, unhybridized pi bond. These pi bonds are going to overlap above and below the plane of that internuclear axis. So I'm talking about it in reference to this sigma bond here. They're going to bond above and below. In this case, I'm writing them side to side. The is your pi bond. And remember, you need both parts of that for your pi bond. So if you need to see them like we wrote them in class, you could draw them this way, see them above and below, but side to side is fine as well. Trying to get my space to work, self-space to work for the next one. This carbon is right here. This carbon is right here. This oxygen is right here. This oxygen is right here. So if I was to match it up to the way I drew that molecule out originally, I would have to move this guy completely up to the other side, but I drew him below instead. It doesn't matter because there's free rotation along these bonds. So it's like I flipped this upside down. There's free rotation anywhere you do not have a double bond. I'm going to move this up and shrink it because I need to be able to write butanone. Okay, so butanone. Butanone tells me ketone. Ketone, I know, has an RCR structure where the R's may or may not be equivalent, and I've got a double bond to oxygen. But tells me 4 carbons. So it's not specifying exactly where the ketone is in this, which makes which I'm just going to write it where I want it then. I'm going to write 4 carbons. One of those carbons that's not terminal, meaning not on the end, has to be double bonded to an oxygen. And then the other carbons will each get enough hydrogens to make them neutral. Or have 4 bonds. Neutral is, I mean neutral by formal charge. But to give them all 4 bonds. Oxygen does have a lone pair here. You don't have to write them, but it does help to see them when you draw out your VSEPR structure, or your valence bond theory structure. Okay. sp3 carbon, sp3 carbon, sp2 carbon, sp3, sp2. So, sp3 is tetrahedral in shape. This is sigma bonded to a hydrogen, sigma bonded to a second hydrogen, sigma bonded to a third hydrogen. This carbon is also sigma bonded to another carbon atom. Which has 2 sigma bonds to hydrogens. That's sigma bond. And a sigma bond to another carbon atom. This carbon is trigonal planar in structure because it is sp2 hybridized. So this is another sigma. These are sigmas. This carbon, this third carbon, is sp2 hybridized. It has a sigma bond to a carbon and a sigma bond to a carbon on the other side. as well as a sigma bond to oxygen. This oxygen is sp2 hybridized. So this is sigma bond, this is sigma bonded, and this is sigma bonded to 3 separate hydrogens. This oxygen has 2 lone pairs. The last thing I'm missing is my pi bonds for that oxygen carbon atom. So this carbon has an unhybridized p orbital, as well does the oxygen. That unhybridized p orbital is going to overlap, forming your pi bond. And that is butanone. Okay, sketch the following using valence bond theory showing sigma and pi bonds and hybrid orbitals. Basically, that's what we're going to do for the next 3 examples. I think there's 6 compounds total. Azide ion. First, you have to remember what azide is. Azide is one of your ions, your polyatomics, N3 minus. N3 minus means 3 nitrogens, 15 valence electrons, negative charge, 16 valence electrons. Right off the list structure, hopefully you find this as well. This is the right structure. So, the 2 nitrogens on the end each are equivalent, and they each have 2 or 3 areas of electron density, so they are sp2 hybridized. The one in the center has 2 areas of electron density, so it's sp hybridized. So what does this look like? Remember, sp hybridized means that it's trigonal planar. So this nitrogen has 2 lone pairs, and then an sigma bond to the central nitrogen. So this is my sigma bond. This nitrogen's sp hybridized. So it's got 2 sigma bonds to its 2 outside nitrogens. That is also a sigma bond. But of course that can't be it, because we also have our P's. So this is also sp2. We have our pi bonds. Nitrogen has an unhybridized pi bond, as does this nitrogen. And these are going to overlap. This is above and below that internuclear axis. But the other nitrogen also has an unhybridized p orbital, which goes, this one's supposed to be like behind the board. This one's in front of the board. This also has that, because the central nitrogen sp means I have 2 unhybridized p orbitals. So this is overlapped behind the board. This is overlapped in front of the board. So that central nitrogen actually has 2 different double bonds. CO2 is very similar in structure to this. CO is in the center, double bonded to 2 oxygens. What we find is that CO2 actually bonds just like this. Got the carbon in the center. Your carbon is sp hybridized. Each of these oxygens is sp2. So sp2 hybridized means that it's going to form trigonal planar. Sp, it's going to be linear. So oxygen each has lone pairs, and then a sigma bond to the carbon. I have to specify that's a pi bond, that's the other half of the pi bond. Pi bond, the other half of the pi bond, and that is a sigma bond in the center. So, just like we saw in the N3 minus ion, we see this for CO2 as well. This carbon actually has 2 unhybridized p orbitals, one above and below the plane of the board, and one behind the board and in front of the board. This oxygen happens to have 1 unhybridized p orbital as well that it uses to double bond to the carbon. And this oxygen also has 1 unhybridized p orbital that it also uses to form a pi bond to that central carbon. Okay, what about 1,2-butadiene? Okay, haven't learned naming yet. You'll learn naming later, but but. So but tells me 4 carbons. Ene tells me double bond. Carbon. Di actually tells me there's 2 double bonds. And 1, 2 tells me where they're at. So I've got 4 carbons. And this is telling me that there's 2 double bonds. One between at the first carbon and one at the second carbon. I'm then going to give this enough hydrogens to make it neutral. Meaning give each carbon 4 bonds. This is sp2, sp, sp2, and sp3. So the first carbon is sp2, which means trigonal planar. I'm going to draw my carbons in first. I'm going to draw my hydrogens in second. This carbon is sp, which means it's hybridized in a linear fashion. My next carbon is sp2 as well, so trigonal planar. And my last carbon is sp4, or sp3. sp4 is not a thing, which means it's tetrahedral. Okay, let's go ahead and put my hydrogens in. This is sigma bonded to a hydrogen. This is sigma bonded to a hydrogen as well. This is sigma bonded to a hydrogen. These are sigma bonded to each other. These are also sigma bonded to each other. This is a sigma bond. Remember, sigma is that head-to-head overlap. This is a sigma bond to a hydrogen. Sigma bond to a hydrogen. Sigma bond to a hydrogen. So I got all my sigma bonds in, but I'm not quite done because I have pi bonds here. This carbon has 2 unhybridized pi bonds. One above and below the plane of the board, and one coming out of the board and going behind the board. It is going to bond. This carbon also has an unhybridized p orbital, which it uses to pi bond to that carbon. That is your pi bond. And this carbon also has an unhybridized p orbital that it uses to pi bond to that carbon as well. And methylamine. Methyl means CH3. Amine means a nitrogen with enough things to give nitrogen 3 bonds. So I've got nitrogen combined with a carbon that's that's singly bonded to 3 hydrogens. That nitrogen wants 2 more hydrogens and a lone pair. sp3, and that nitrogen is also sp3. So the carbon, sp3 hybridized, meaning that all of these bonds are equivalent. Nitrogen is also sp3 hybridized. Okay, so this is a sigma bond that's formed between the carbon and nitrogen. This carbon also forms a sigma bond to a hydrogen, or 3 technically, 3 different hydrogens. This nitrogen forms a sigma bond to 2 different hydrogens and has a lone pair in its last orbital. And to finish out this chapter, Ch3cho and Xef4. Remember, the way these are written is telling me how it's connected. An H3 following a carbon means the hydrogen is bonded directly to that carbon. So this tells me I have CH3 connected to a carbon, which has a hydrogen, and then an oxygen. Why did I double bond that? Because carbon only has 1 hydrogen and 1 carbon attached to it. It needs 2 more bonds. So it's going to have to double bond to that oxygen. Draw out the Lewis structure, you get to the same point. sp3, sp2, sp2. So that first carbon is sp3 hybridized. I'm going to draw in all my bonds to my carbon and oxygens first. My sp2 hybridized carbon has a sigma bond to that carbon. It also has a sigma bond to my oxygen. That oxygen has 2 lone pairs in its other orbitals. That carbon has a sigma bond to hydrogen. This carbon has 3 sigma bonds to 3 other hydrogens. But I'm not quite done, because this central carbon here has an unhybridized pi bond that is going to bond with this unhybridized pi bond from the oxygen. And that is where I form my pi bond. And Xef4, we've drawn out Xef4 already in the practice, so if you're not sure why, go back and look at that. But you should find that Xef4 forms a square pyramidal structure. There are 1, 2, 3, 4, 5, 6 areas of electron density, which means I need S, P, 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 D, D, or sp3d2 hybridized. So I have 6 orbitals that are equivalent off of that xenon. This is a lone pair, and this is a lone pair. And the xenon will head-to-head form a sigma bond overlap with the fluorine. Again, why am I not hybridizing my fluorine? Because fluorine can only bond with its p orbitals. It's the only spice that it has left. But all of these are sigma bonds. And that is the end of your additional practice for chapter 11. I hope this helped. Good luck.